Hello and welcome back to another A-level and IB chemistry tutorial with me, Miss T. This lesson is on assigning oxidation states, so can be found in the redox topic across all A-level specifications and IB. We'll start with definitions, some rules and worked examples, and finish off with some practice questions for you to try. Now, full disclosure, oxidation states are not real. Okay, they are the hypothetical charge of an atom if all of its bonds were ionic. And the reason that we assign oxidation states is because it's easier to track the loss and gain of electrons in redox reactions using oxidation states rather than to try to look at formal charges where sometimes species might not have an actual charge. When we write oxidation states, we write them similarly to how we would write a charge, except we always write the sign before the value. So for a charge, we would say 1 plus or 3 minus, whereas for an oxidation state, we would say +1 or -3. So let's get into the rules of how we assign oxidation states. Now, any atoms in an element will have an oxidation state of 0. So for example, a chlorine molecule, just an element, so each chlorine atom would have an oxidation state of 0. Carbon in graphite, oxidation state of 0. Any metal just by itself, oxidation state of 0. Rule number 2 is in a simple ion, the oxidation state is the same as the charge. So we know that in group 1, our metals form 1 plus ions. In group 2, they form 2 plus ions, and so on and so forth. So the oxidation states of these ions would be the same as their charges. So Na plus would have an oxidation state of +1, S2 minus would have an oxidation state of -2, for example. Rule number 3, if we are dealing with a compound, the oxidation states of the atoms in that compound must add up to 0. So if we look at Na2O, sodium oxide, as an example, the oxide ion has got a charge of 2 minus, and so an oxidation state of -2. The sodium ion has a charge of 1 plus, and so an oxidation state of +1. And with two of those, they are contributing +2. +2 plus -2 gives us 0 overall for the whole compound. Rule number 4, if we are dealing with a complex ion or a polyatomic ion like sulfate, hydroxide, manganate, nitrate, for example, all of the oxidation states of the atoms must add up to the total charge of the ion. So instead of adding up to 0, as we did with the compound before, they have to add up to whatever the charge of the ion is. So in this case, for sulfate, the individual oxidation states would have to add up to -2. So oxygen in compounds is nearly always -2, and we've got 4 of them, so that's contributing -8. That means that the sulfur must have an oxidation state of +6, so that the +6 -8 gives us a total of -2. And finally, some bonus rules and the exceptions to those rules. First, as we saw before, oxygen almost always has an oxidation state of -2, except when it's in a peroxide. So for example, hydrogen peroxide, H2O2, where it has the oxidation state of -1. Or when it's bonded to fluorine, which is the only element that's more electronegative than it, where it has the oxidation state of +2. Hydrogen almost always has the oxidation state of +1, except when it's directly bonded to a metal in a metal hydride, where it has the oxidation state of -1. The halides, so fluorine, chlorine, bromine, and iodine in compounds, almost always have the oxidation state -1, although saying that they really don't. Fluorine is actually the only one that is always -1. The other three could be +1, +3, +5, or +7. So we would have to work it out based on the oxidation states of what they're bonded to. Fluorine is the only one that is always -1. And finally, transition metals in compounds. As we know, they have variable oxidation states. So that would be given to us as the Roman numeral, or we'd have to figure it out from scratch because we can't determine it directly from the periodic table. So it's now time to practice applying those rules to some practice questions for yourself. So assign the oxidation states to all of the atoms in the following compounds and ions. Pause the video now and press play when you're ready with the answers. So for our first two, just elements, so always 0. HBr, hydrogen, is almost always +1, which makes the Br -1. And in water, H is almost always +1, oxygen almost always -2, and they add up to 0, which works. For our next ones, slightly trickier. So sodium in group 1 would have an oxidation state of +1. Oxygen would have an oxidation state of -2, so that the total oxidation states add up to 0. The chlorine would have to be +1. In HClO2, again, hydrogen is +1. The oxygen is -2, but there are two of them, so contributing -4, which means that the chlorine must be +3. NaClO3, the sodium is +1. The oxygen is -2, but there are three of them, so contributing -6. So the chlorine must be +5 to make the total add up to 0. And finally, SF6, fluorine is always -1, and there are 6 of them, making it up to -6. So the sulfur must be +6. And our final trickiest questions. So for our ions, first the phosphate ion, the oxygen is -2 and there are 4 of them, so -8, which means that the phosphorus must be +5. For manganate, the oxygen is -2, but there are 4 of them, so -8, which means that the manganese must be +7. For nitrate, the oxygen is -2, but there are 3 of them, so -6, which means the nitrogen must be +5. And finally, in chromate, dichromate rather, the oxygen is -2, but there are 7 of them, so -14, and so the chromiums must add up to +12. There are 2 of them, so each one must be +6. So how did you do? Leave a comment with any topics that you really want covered next, and I'll see you next time for another A-level and IB chemistry tutorial. Bye.